All right, welcome back to the deep dive. We're all about getting you up to speed quickly,
Yeah,
right?
Ellie. No time wasted.
So today, we're going deep on something pretty fundamental. We're talking about liquid extraction, LLE.
Yeah, one of those essential processes. You need to know this.
For sure. It's all about taking, say, raw material from your fermentation and getting that pure product out.
Right, right. The notes you've got here, they highlight that LLE. It's also called solvent extraction. It's like super important for all sorts of downstream processing. So what we want to do today is like give you a solid grasp of the workings,
Mm,
different techniques, the choices you got to make, kind of like a cheat sheet for mastering this core separation thing.
gotcha. So liquid, it sounds pretty basic, but it hinges on something we all know. Certain liquids just won't mix, like oil and water, right?
Absolutely, you nailed it. And the thing is, when you have two of these liquids that just don't want to mingle, and you throw in a third substance, it's going to distribute itself between the two.
Okay, so it kind of picks a side, you're saying.
Yeah, exactly. It's called partitioning. And what's crucial here is something called the distribution coefficient, or KD. Basically, it's a ratio telling you how much of your target substance is hanging out in one liquid versus the other. And usually, a higher KD in the solvent you picked, that means it's pulling more of what you want.
So if it's pulling more, that means it's more efficient, right?
Exactly. And even tiny differences in this KD, they can become huge when you're doing extraction multiple times. Like repeat, repeat, repeat.
Okay, interesting. So it's about like finding a solvent that your product really prefers way more than all the junk you don't want.
That's the whole game, yeah.
Yeah.
Selectivity. If your target compound has a way bigger thing for your solvent, like a much better KD than all the impurities, well, that's when you get a clean separation.
Cool. So how does this preference actually play out? How does the stuff actually move from one liquid to the other?
It's all about mass transfer. The more those two liquids can touch, the faster things go. Think about shaking a bottle of salad dressing, right? More contact. Then there's how easily the substance can scoot through those liquids, its diffusion, and how thick or gooey the liquid is, its viscosity. Oh, and warmer temps usually help things move faster too.
So if you're in a lab versus like a giant factory, how do they actually do this in practice? What does it look like?
Well, the scale really dictates the method. If you're in a lab, you might grab a separatory funnel, mix it up, let it settle, then separate those layers. Batch extraction, they call it. Simple for smaller quantities. Now, on a big industrial scale, it's usually continuous countercurrent extraction. Imagine two liquids flowing in opposite directions in a column. It's all about maximizing contact, making it super efficient.
Makes sense. And then there's that supercritical fluid extraction thing I came across. Oh, yeah. Supercritical fluid extraction, or SFE. It's sometimes a greener way to go. It uses things like carbon dioxide, CO2, under super specific pressure and temperature. And here's the cool part. It's like the CO2 takes on properties of both liquids, A and D gases. You can actually tweak its solvent power just by adjusting the pressure and temperature.
Wow, okay, so back to the beginning. How do you even pick the right solvent? It seems like there's a lot to consider.
Oh, absolutely. Like we've been saying, you want high selectivity, good KD for your target. But it can't mix much with your original liquid, right? And then you got to factor in safety, low toxicity, not flammable. Cost and availability are always realities. And ideally, you want something that won't form those pesky emulsions, where they get all stubborn and refuse to separate.
Right, right. So you've got your solvent, it grabs all the good stuff. How do you get the solvent back to use again? A and D get your purified product. You've hit on a crucial point. Recovery efficiency. That's key for cost and being sustainable. Distillation. That's common for those solvents that are volatile. They evaporate easily. You can also use evaporation or use gas or steam to kind of strip the solvent away.
Mm.
Or there's adsorption where you use stuff like activated carbon to grab it. Oh, and then there's membrane separation and even back extraction where you basically transfer your precious solute back to another liquid. Lots of options.
Wow. Okay. So to sum it up, LLE is all about using these liquids that don't play nice, immiscible liquids to pull out what you want. It all comes down to how soluble it is in different stuff. And the key is picking and recovering your solvent wisely.
You got it. And if we zoom out and look at the bigger picture, think about purification. It's the foundation of so many industries, from making those life-saving meds to even producing the food we eat. And LLE, it's a foundational tool to make all that happen.
So thinking about all this kind of brings up a final thought for you, listener. With all these things to juggle when picking a solvent, making it efficient, environmentally sound, and all that, what do you think is the toughest challenge in designing a liquid extraction process for, say, a brand new pharmaceutical? Something to chew on. Thanks for taking the deep dive with us.